This is Daniel Coosbury, and we're going to keep looking at frequency distributions for quantitative data in this video. So I showed you how to make frequency distributions in another video. This one is going to focus primarily on numerical data now rather than categorical data. But the way we do it with numerical data is because we're not just dealing with a list of names and things like with qualitative data, now we just have a whole bunch of numbers that instead of just counting up the frequency of each kind of number, what we like to do is we like to make categories for the numbers, which we call classes. So this is what classes are. Classes are intervals of equal width that cover all the observed values in the data set. So I'm going to show you an example in a second. This is an example of a frequency distribution for quantitative data where the classes are defined here. So this would be all the numbers in the data set from 0 to 5. We'd count up how many fit in this class. There was 3. I just made it up. And this is how all the numbers from 6 to 11. This is the frequency of the numbers that fit that bill. So this would be an example of classes. So classes are intervals of equal width that cover the observed values. The lower class limit is the smallest value in a class. So in this case, the left numbers will be the lower class limit. 0, 6, 12, and 18 are the lower limits. The upper limits are the largest value in each class, 5, 11, 17, and 23. So these are upper limits. It looks like I'm dealing with a discrete data set because if I had the number 5.5, it wouldn't really belong in any of these. It looks like just the counting numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's just assume this is discrete. And the class width is going to be the difference between the consecutive lower class limits. So this is a little bit of a confusing definition, but let me show you what this means. These are consecutive lower class limits. That's a lower limit. That's the next one. That makes them consecutive. The difference between these two numbers, you can find by subtracting them, is just 6. I'll double check and make sure I did that right. The difference between the consecutive lower limits is the difference of those two numbers, which is also 6. And if you do 18 minus 12, you get 6. So in this case, the class width is 6 because I found it using this definition. The difference between the consecutive lower ones. The class width is 6. So this is an important definition because this is the only way to find class width. My first encounter with this, what I wanted to do, I wanted to take the difference between the lower limit and the upper limit, in which case you get 5 instead of 6. That's technically incorrect. The class width is the difference between the consecutive lower limits. This is how you get 6. So what that's saying is it's telling you how wide the interval is or how many values can go in it in this case. So in this case, I can get 6 values in here, 0, 1, 2, 3, 4, and 5. That's 6 numbers. I can get 6 numbers here, 6, 7, 8, 9, 10, 11, 6 numbers, and so on. But the technical way to find it is to do what I did here. So that's an example of a frequency distribution. You break the data set up into groups, and then you count the frequency of the ones in each group. Now, when you're doing this for the first time with a data set, you've got to make decisions like how big are my classes going to be? Where should I start? These are just some suggestions for deciding what your classes should be like. So for instance, we want to make sure we make classes so that all of our data fits into one of the classes. So if we stop too soon, we may miss the largest number, or vice versa. If we may lose the smallest number if we pick a wrong starting value. So we want to make sure we include everything. We also want to make sure the classes don't overlap. So for instance, here, there's no overlap. Like this goes to 11, and then 12 starts, and then 17, then 18 starts. There's no overlap. And then this is probably the most important part when you're making a frequency distribution. And we'll make histograms in a little while. For the distribution to represent what you want it to represent, then the classes need to be of equal width. So in the last example, the width was 6 every single time. If they're not equal width, then what you end up doing with your table is you make categories, some are bigger than others, and your table's not going to tell you what you want it to tell you. The equal width is going to allow you to see, okay, well, in this 6 number range, there was 9 things. In this 6 number range, there's only 3 things. The widths have to be equal so that you can actually compare them to each other. Like if this was a 6 number range and this was a 20 number range, And these numbers don't have a lot, like they're a lot harder to interpret. But I can say in this 6 number range, there's 8. In this 6 number range, there's 2. And I can do that because the classes are equal. We also want to make sure there's no gaps. So we don't want to leave any number out, even if they're not in the data set. So in this case, if this is a discrete data set, just the counting numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, then there's no gaps. But if it was continuous and numbers like 5.5 might exist, I should make my upper limits different. So let's just assume this is discrete. I'll show you a continuous one in a little while to show you how you make sure there's no gaps. Okay, these are the steps for constructing a frequency distribution. I'm not going to read these out loud. I'm going to go ahead and do it, but feel free to pause this video and jot this down or come back to this when you're working on things. But there are the steps. And then I'm going to show you how to do a frequency distribution with this example. So here's a data set, and I tried to make it look ugly because the point of these sections are to make ugly data sets look meaningful. So turn them into nice looking tables or nice looking graphs that can show you things. So this is a good example of a continuous data set because we've got decimals and we never run out of decimals, so this will be continuous. We've got the emissions of 65 vehicles in units of grams of particles per gallon of fuel, and we want to construct a frequency distribution using a class width of 1. So we don't have to decide the class width in this case. It's decided for us. So let's look real quick at the data set. We want to make sure we include all of the data when we make our frequency distribution, which means we want to make sure we capture like the biggest number and the smallest number. So as for the smallest number, I see a 0.25 over here. I don't think anything smaller than that. So we need to make sure our smallest class could include that. And then as for the largest numbers, I see a 6.64. Is there anything larger than that? I don't think so. But if I can find my max and I'm in, then I know that my lowest class should include that. My highest class should include that. And then everything else is between them. So I should be able to make classes now with width 1. So my width is supposed to be 1. Let's start. I like things that look nice. Let's let our first lower class limit be 0. And the width's going to be 1. So this will go from 0 all the way to some number, and I'll figure out what that number is. So I'm following these steps now. The class width is 1. That was given to us. The lower class limit, the first one's going to be 0 because I want this class to contain 0.25, which is a little bit bigger than 0. The second lower class limit needs to be exactly 1 unit bigger than the first lower class limit. So whatever this number is, this minus that needs to be equal to 1. So this number needs to be the number 1. So 1 minus 0 is 1. That gives me exactly what I want. I don't know what's going on with this little circle thing, guys. And then I'll fill in the remaining limit. So you see, we have a class width of 1 now because 1 minus 0 is 1. And then they all need to be the same size. So then the next lower limit needs to have give this a width of 1. So 2 minus 1 is 1. That's really nice. So I'm just going to fill this out now. So these are my lower limits. And I think my biggest number was 6.6 something. So if I go up to almost 7, then this will capture that biggest one. So now I need to put numbers, upper limits, to make sure I don't leave out any possibilities. So will it make sense if I let my first upper limit be 0.99? How do you feel about that? So the reason I picked it is because all of my data were out to 2 decimal places. And this is the biggest number with 2 decimals, short of actually being 1 itself. So this is going to be my upper limit. So that's kind of nice. And then I'll do the same sort of thing for all of my other classes. So I'll let 1.99 be the next upper limit, and then 2.99, and so on. The hardest part about this is getting started, picking your first few things. Once you get started, there are going to be patterns that show themselves anytime you work on it, whether your class width is something easy like 1 or harder like 6. But this would be these are going to be all of my classes. So this will be part 1 of my frequency distribution. This will be the class part. And then the frequency will be the second part. And then you'll end up making a table where you count everything and put them into classes. Now, I'm not going to do that for you on the video. I'm just going to go ahead and do it and say, here, there are the frequencies. So here are my classes. They're my lower limits, they're my upper limits. You see all these have width 1, because if you take the difference of the consecutive lower limits, you get 1. And then these are the frequencies in each class. So 26 of the data points fell between 1 and 1.99, and so on. So that is how you make a frequency distribution with numerical data. You start by building your classes to capture the whole range of the data set, and then you start just putting things in classes. And that's what you do. We can also make relative frequency really, really easy with quantitative data, just like with qualitative data. So if you remember, relative frequency was the frequency divided by the sample size. If we already have this just from counting things, then all I've got to do is take each frequency and divide by the sample size, which is 65, and that's where those decimal numbers come from. So if you take each number, divide by 65, you get the relative frequencies, and you'll see things like, okay, well, the biggest class had 0.4 of the data in it, so that's the proportion. So that's like 40% of the data in it, whereas the smallest class had like 3.1% of the data in it. So having the relative frequency is really nice. I'm sorry, that's not the smallest one. That's the smallest one, 1.5% of the data. So relative frequencies are really useful. And once you have the frequency distribution, listen, these are not hard to find. You just divide by n, each number by n, and you get the relative frequencies. I think a rule of thumb with relative frequencies has to do with rounding, has to do with how many decimals your data goes to already. But I may be wrong. I think the rule of thumb is, since my data goes to 2 decimals already, you just add a 3rd decimal when you round your relative frequencies. I'm not entirely sure. But anyway, there's that. So we can make frequency distributions once we have the classes. We can make relative frequency distributions once we have the classes. I hope that so far in this video you think the only thing that's really challenging is making the classes from scratch, and that's kind of tough. Everything else is the same thing with categorical data. There's a nice thing that I really like that you can do only with quantitative data. So this is a completely new thing. It's called a cumulative frequency distribution. And what it does is it expresses the frequency of data in classes that are lower or equal to that particular class. It's a really kind of frustrating definition, but what it means is with cumulative frequency, it counts not only the frequency of that class, but also how much we've accumulated. How about that? Accumulated all the way up to that class. So the idea in cumulative frequency will be as we go on to bigger and bigger numbers, bigger and bigger classes, our frequency is just going to grow and grow because we're just going to keep accumulating the old frequencies. So let me show you how you do this. The math's really not hard, even though the definition might be kind of weird. So the cumulative frequency for the first class is going to be just the frequency of the first class. This is a little ridiculous. The frequency of the first class. In other words, this is how much data is in that class or in lower classes. Well, there are no lower classes, so it's just going to be that class. The next cumulative frequency is going to be what's the frequency of this class plus all of the lower classes, which is going to be that one. So I'm just going to take 26 and add 9 to it, and I get 35. So that's the cumulative frequency of the second class. It's going to be this one plus all the classes that came before. So it's really not hard to find. We're just going to add 26 and 9. The next one, I'm going to take the frequency of this class, 2 to 2.99, and then add the frequencies from the class below it. So the cumulative frequency would be all 3 of these numbers added together. I'm going to make it easy on myself and say, oh, I'm just going to add that to the old cumulative frequency and say, okay, well, that's going to be 11 plus 35, 46. So you see what's going on is we're accumulating more and more things as we go. And eventually we should end up with 65 down here. The last cumulative frequency should be the sample size, but we'll see. The next one's going to be 13 plus all the ones before it, which is 46. So 13 plus 46 is going to be 59. The next one's going to be 3 plus all the ones before it. 3 plus 59 is 62. And then 1 plus 62 is 63. And then 2 plus 63 is 65. So what these numbers are telling you is when you get to class 2.2 to 2.99, this is not only how much is in the class 2 to 2.99, but also how much is less than that. How much is like 1 and 0 and things like that. So it's really nice when you're starting to represent data, when we start working on probability distributions, that how much you accumulate over time is a really useful thing. that people like to use. Anyway, I hope you see in this video that making the frequency distributions and the relative ones for numerical data is hardly any harder than doing it for quantitative data. The big trick is deciding what your classes should be and making them first, and then just making your frequencies. So this is the stuff that you'll need to work on in particular with this thing. And once we get this done, we'll be able to make histograms, which is what I think is the best part of this chapter. It's the most useful thing. And so we're going to use frequency distributions in just a little bit to make histograms.